Welcome to Top of the Line. This is the podcast version of our YouTube show. New episodes every Monday and Friday where we talk about audio and hi-fi related themes.
If you have any requests for a future episode, send us an email, totl@abyssheadphones.com.
Well, we're back with questions off the internet. And if anyone out there has any questions for us, you can send it to us at totl@abyssheadphones.com. Maybe we'll answer in our future episode. So this one reads, Hi guys. Hi. My second question, following the one on vinyl noise. The only well-advertised example of the adoption of acoustic metamaterial in loudspeakers is that of the KEF LS50 Meta. Do you know of any manufacturer using metamaterial absorption technology in the world of headphones, and more importantly, do you think it could be used to produce a closed back without the unwanted reflections? Well, we have some vague experience with this. In fact, we talked about this before, but our very first attempt with the planar magnetic driver of 1266 was closed.
I know. Forgot about that.
We kind of had something similar to what KEF is using. They have a little video describing it, and they show you pictures and stuff like that, and animations. It looks cool. But we did something similar to that.
I don't think it was as well thought out as theirs.
Well, it was more layers we were doing.
It was a stacked wood design, laser cut.
Yeah, right.
Yeah. It was an attempt.
Yeah, where each layer, as you've gone deeper into it, each layer absorbed. The first layer was the least absorptive, covered some for certain frequencies, let most through to the next layer and the next layer. And the idea was that as it sifts through layers, you would lose more and more of the frequency, the various frequency, what would you call it?
Snippets you dissipate the energy over time.
Yeah, right, till the very end.
It's the same concept as anything. When you have energy and you're trying to get rid of it, getting rid of it all at once tends to be much more difficult than getting rid of it slowly.
Yeah, well, in a wide-banded situation.
Right. In
narrow
this case,
band, it's easy, but
in this case, we need to handle a wide spectrum,
including
we need
the
to handle
bass.
everything.
That was the problem.
Everything coming off the back of the driver. Low frequencies all the way up to high, and that's challenging to do. I believe they're doing this on, what is it, a tweeter?
The tweeter. It's a tweeter that's in the center of the, it's in the center of the woofer.
Yeah, so they're not dealing with 5 hertz
it's
to
just
20 kilohertz.
It's just the back wave of the tweeter. Yeah.
Right.
No, this thing wouldn't work at that. They have actually they throw a graph up on one of their videos about the.
It shows you the
attenuation. It kicks in around 600 hertz and goes. It's very effective at 600 and up, but below that it drops it drops pretty quickly.
Right. Yeah. Well, you could design these for any range.
Fiberglass and stuff are similar too. When you look at a lot of the fiberglass materials, certain insulation materials, acoustic materials that are used for room acoustics or for inside speakers, they vary like that too. It's very similar. It's just this is, I think, a more compact method of doing it.
I guess one good thing to bring up is why this is done and the problems with the conventional methods. So traditionally, you have on a driver that's producing audio in a headphone or pretty much anything, you have audio coming out both sides of the driver. Typically, it's pretty balanced, more or less.
Front and back, basically.
Yeah, so the side you hear, there's also audio coming out the back. That's effectively the opposite of what comes out the front. And you want to get rid of that. Otherwise, in a little shell, it bounces around, causes issues. It could actually distort what's coming out the front end by bouncing around and reaching the front at a different time. So you want to ideally just dissipate it, just get rid of it. That's why open backs tend to perform better than closed, because they pretty much just throw that right out the back. They don't bother dealing with it. It's pretty much just gone for the most part.
The back wave goes out the backside.
You just throw it out.
Unfortunately, most open backs aren't that open. So
they're not that open.
A lot of it sticks around, and that's what messes with you.
The trouble is, people typically stuff stuff inside of the headphone to try to deal with the frequencies that I have problems with. And it's things like this, soft things, insulation, whatever, foams, felts, etc.
Absorptive materials.
Yeah, and it helps absorb and dissipate this energy. However, they only work over relatively narrow frequency ranges.
Right.
So they don't work for everything. And now you're absorbing well, but maybe in this one region. And you're not absorbing in every region perfectly, and it's never perfectly even and flat.
And you're absorbing in areas where you don't want to absorb.
Sometimes, yeah. You can't pick the exact absorption characteristics.
Yeah.
But with a metamaterial, or at least what KEF is calling a metamaterial, which is interesting marketing term.
Yeah.
But what they're calling it, you kind of can. You could engineer something that's designed to absorb exactly the frequencies you want in the right quantities.
Yeah, in more or less a flat response.
More or less.
We watched their video on it on their website. It was kind of cool. It's a short video, but if you know what you're looking at, it's pretty obvious what they're doing.
Well, they do reference that it would take a meter long tube or whatever to do the same thing. So I guess the best example of that would be the Bowers and Wilkins Nautilus speakers.
Yeah.
Very clear cut from the outside what's going on with them. Each driver has its own tube at its own length, and as you get down to I believe it's a 15-inch driver, you need a huge tube. So
basically a conch shell.
Everything's got its own
I don't even know.
individual tube.
What would you call that shell? It's not a conch shell.
There's a name for it.
It's a circular,
Nautilus?
Yeah,
It's a
well, I
Nautilus.
guess it is a Nautilus. Yes, of course.
Okay.
Which probably follows the golden rule, right? In
The
terms
golden
of
ratio,
golden
yes,
ratio.
of course.
Yeah, right. Thank you, George Cardis, for he's always followed that rule with a lot of his cable designs and so on.
Yeah, even the
it's one of his
conductor
things.
layup, which is interesting.
Yeah, so there's something about that, I guess, in nature that strikes a chord.
Apparently.
Yeah.
Yeah.
But
That's the easiest one to view from the outside, though.
yeah.
Because with the cap speakers, you obviously can't tell what's going on.
Well,
on
that's
the
true,
inside.
and and looking at it too, you'll see what extremes you'd have to go through to deal with the back wave on a driver, and
well, in the bass especially.
yeah, right, and especially in the low frequencies, and that's something to explain. That's the hardest thing to absorb, regardless of whether it's a small device or a room. You start dropping below 150 hertz or so, or even below 100. You need foam 3 foot.
You need
thick
a lot of volume.
to absorb. 30 to 50 hertz range is really difficult. Those are trick. You can't just do it with. You can't just throw a piece of foam on the wall and absorb that range. You need tuned devices.
It'd be nice if you could.
It'd be nice if you could.
Put this foam in there.
Some people do it. I've seen the people put in these corner things in a room, and we're talking they're out 3-4 feet, and they just stuff the thing with wool. And the idea is, sooner or later it'll absorb it. There's so much of it.
Yeah, if you have
the
the
low
space,
frequency energy going through will slow down at some point.
Doing that in a headphone is very problematic.
Yeah.
So not
you
quite
don't have 4
practical.
feet.
And I guess we could explain that briefly to people that don't understand. But what you're doing with absorption is, technically speaking, is you're taking an acoustic wavefront, and converting it to heat. You're somehow taking it, and you have to slow it down, and then basically you're offering resistance to an acoustic wave, and the resistance dissipates it as heat. Of course, it's not something you're going to sit there and measure, but it doesn't make the room hot, but that's what effectively is happening.
Yeah, it's trivial amounts of energy, but you got to deal with it somewhere. Otherwise, it comes back, bounces around, causes all kinds of issues in the room or your headphone or your speaker. So dealing with it is a big problem. And what CAF is doing is interesting. It's a different approach to what I think is intrinsically obvious to anyone in the art, but they're implementing it in a very different manner. So that's unique for sure. But I think other people have likely attempted this, I would assume, in the headphone space. I don't know anyone going to that great length, because the trouble is it would be very challenging to fit a broad spectrum absorber like that.
Well, that's the issue.
Into a headphone, because you need to go way down low all the way up top. And the higher frequencies, it doesn't take up that much space to absorb. But the low, unfortunately, it does.
Yeah, it would have to be a lot thicker.
It's just kind of the math of it.
We were just talking about that too, where they're dealing with. If you look at the construction of this meta absorber they're making, it's a sandwich. It's we'll have a picture up here, but it's basically it's 2 plates with a certain thickness of foam or something in between.
Yeah, and the plates form a tube then.
Yeah,
So
right.
it's just bouncing around that tube.
And everything that's bouncing is going back and forth between the plates, if it does bounce, and is absorbed by the foam layer in between. And the other thing we're looking at it too is it's really made specific for that driver, their tweeter.
Yeah.
It's made because the tweeter and the woofer are one in the same cabinet. So, if you just let it fire into the rear of a cabinet like most speakers do, there's no good way to isolate the back wave of the tweeter from the woofer.
Yeah, they're coming from the same point.
Yeah, right, same driver. So here they kind of made basically a custom sandwiched absorber that deals with the back wave of the tweeter and isolates it, at the same time isolates it from the woofer. Because woofers, if you load them into the same cabinet, the woofer will modulate the tweeter, right? You're pressurizing a cabinet,
Right.
so the tweeter's going to if it's open to the back, the tweeter's going to move too a little bit. It's affected by the bass frequencies, and you know, you normally don't want that in a higher end speaker.
Yeah.
You don't want that in any speaker, but
No.
I would assume they just do this to create a larger internal area, right? Like the sole motivation is just so you don't need a divider, which means for the size of the speaker, you have more internal volume.
it's a bookshelf. So
Right.
yeah,
In
that's
a
what they're
bookshelf,
doing.
that's
right.
important.
There's no good way to deal with it.
But you could do it in a big speaker. You could do it just by putting a divider there, and as long as you have enough volume on both sides, if you just have a standard two-way design, you could totally get away without this. It's just this is a novel approach to kind of giving more space inside,
Yeah.
like a TARDIS, I guess.
Good marketing. Yeah, like a TARDIS. Yeah, it's bigger
Yeah.
on the inside. Yeah.
Yeah, I guess if you have unlimited space, then you wouldn't necessarily need to do something like this.
Yeah.
I mean, you just separate everything.
You would just put a long tube off the center of that driver,
Make it
and
3
just
feet long
dissipate the back wave of the tweeter and
But yeah,
at some distance.
that doesn't work in a bookshelf.
Yeah, right. Yeah, it's a good idea. Now, the question was, can you implement this, or does anyone implement this in the headphones? And I think you partly answered that in the fact
Kind of
that
yes and no.
you can't really do this won't help with the bass frequencies.
Yeah.
It doesn't have anywhere to really go there below 500 hertz or so is really difficult, and that's with a closed back. That's kind of the biggest problem is
Bass.
if you
Always with the
don't
bass.
get rid of that bass back wave, it cancels out the front bass wave, and you wind up with no bass,
Yeah.
which is a problem with closed back, I think, in general.
In general, yeah. It's
Yeah.
very challenging. The bigger the volume you have behind the driver, the easier it is to deal with. So that's why a lot of times you see closed backs that are just physically large because it's easier. It's very difficult to make a very, very small closed back perform exceptional.
I guess the biggest problem is in a headphone application, especially in a planar magnetic where the driver is physically large. It's like the size of the device you would need to actually be effective
Oh,
would
right.
be so big, it would be bigger than the driver itself.
Yeah.
So you'd have like a
Yeah, you have a headphone like this, and you got a metabsorber
Yeah.
that's 3 times the diameter of it.
Yeah.
Yeah,
Yeah.
yeah,
So
that's
it would
true.
be very effective, but at that point, is it really closed anymore? Because it's all the benefits you were looking for are gone. It's gigantic.
Yeah, right.
So if you're only looking to minimize leakage, well, you could just go in a sealed room, and that works pretty well too, right? And you're kind of getting there with with something like that
Yeah.
to solve all your problems for you on the back of the headphone. It's tough in the volume allotted.
Yeah, and I think what we found, what we're finding too, as we complete our closeback project, is that you're better off with using a combination of absorption and diffusion.
Yep.
And and if you can reuse that energy, and especially in the low frequencies, and keep it, or in some way, it's even better. But primarily, yeah, in the low frequencies in a closed headphone, you're kind of trying to get rid of the back wave entirely. That's the challenge. Dealing with the highs isn't so bad. There's all kinds of ways to do
Basically,
that.
what they're doing in that design is already done in headphones. Most headphones on the market, especially the high-end headphones, have some degree of design of that nature. They do it in a very different manner, and it's not an entirely sealed system because they have different reasons for doing it. But it's not to say it's not done. It is. It's just they're targeting specific frequencies that are a problem in their enclosure. You see all kinds of like weird bumps, nodules, and wave alignment type
Yeah.
deals to try to direct energy where you want it to, or you have some sort of stuffing inside the shell or foam or some sort of fibrous material that's designed to target a specific frequency range. So it's basically the same thing. It's just what KEF is doing is designed to cover more or less the entire frequency range that Tweeter puts out.
Well, more importantly, it's made specifically for that particular concentric
Yeah.
driver they
For
have
that
there.
very device.
So it's not really, the bottom line is you can't transpose it to, it's not easy to transpose to a full range.
well, not the same
That's
thing.
all.
It'd have
Yeah.
to be custom made for each application.
Yeah, and again, we're probably back to that layer thing like we were talking
Right.
about before, where some frequencies deal with that, and another device deals with the lower frequencies, and then you're compiling things into a small package that you can't fit. So yeah,
As of yet, nobody does something on that level because it's just physically too large.
there's not enough room. So that's it. That's as good as we could describe, I guess, in a rather lengthy video it turned out to be.
Yeah.
So anyway, everyone, thank you very much for watching, and please subscribe to us and give us a thumbs up anytime. Take care.